This video introduces a lesson found in Unit 7, Rational Functions. It is actually the second lesson within a larger lesson referred to as Graphing Rational Functions. The actual name of this lesson is In Behavior of Rational Functions. If you look in the teacher pages of the actual lesson, not the scope and sequence, you'll see these teacher notes that discuss what the end behavior is. And this is a good idea to mention this to the students, that end behavior just describes the behavior of the function as your x's are going to positive infinity or negative infinity. So as your x's are going off to the right or to the left, what are the y values doing? Are they going up towards infinity, down towards negative infinity? Are they approaching a line? What are they doing? Now, something else you need to remember about in behavior asymptotes is they simply tell what's going on each end. It does not tell what's going on in the middle. So sometimes the function can cross these asymptotes. Okay, that's what this paragraph is talking about. Now, 3 types of end behavior asymptotes are listed down here for you, and when they happen. You may want to hold off on telling this information to the students, though, because there's a question in the assignment that uses these 2 right here, when you have a horizontal asymptote and when you have an oblique asymptote. So let's finally get into the lesson. I actually want to work through problem number 3 with you. If you'll notice, the first 3 problems say determine the horizontal asymptote by evaluating the limit as x approaches positive or negative infinity. Now, we have not gone over any limits yet, so you'll just need to remind them. That simply means as your x's are going off to the right, getting really big, or going off to the left, getting really small, what's happening with your y coordinates. And this is where I bring in what I call the HA rules, which just stands for horizontal asymptote. So let me show you how I refer to the horizontal asymptotes and how to find them. Again, I call this HA rules. And what I tell the students we need to do is, the whole point of this is we are going to compare the dominants of the numerator and denominator. Now, there's 3 ways that these can compare. The first way is what I call top-heavy. This is where the numerator's power is going to be bigger than the denominator's power. Now, there's an acronym for this that you can use, which is BO2. This stands for big on top is undefined. That means there is no horizontal asymptote. We're going to have to do something different to find the end behavior asymptote, and we'll discuss that in just a minute. The next comparison, it could be bottom heavy. This is where the denominator is more dominant than the numerator. In this case, you would have a horizontal asymptote, and if the denominator is getting bigger than the numerator, that means the fraction is getting really small, so small that it's going to approach 0. So you have a horizontal asymptote at y equals 0. Now, the acronym for this is BOBO, which stands for big on bottom is 0. And then the third comparison is they could be the same. This is where the numerator's power equals the denominator's power, and in that case, you do still have a horizontal asymptote, and it's going to be at y equals the ratio of the leading coefficients. Now the acronym for this comparison is BETC, which stands for bottom equals top, use the coefficients. The students really seem to like these acronyms because not only does it tell what is going on with the function, whether it's top heavy, bottom heavy, or same, but it also tells what it is. So if it's top heavy or big on top, it's undefined. There is no HA. If it's bottom heavy or big on bottom, then it equals 0. And if it's the same or the bottom equals the top, then you use the coefficients. So let's apply these HA rules. We're going to work out number 3. And number 3 tells us that we have the function y equals x squared plus x minus 2 over x squared plus 3x minus 10. And we want to find the horizontal asymptote and see if this function intersects its horizontal asymptote or not. First of all, we notice that the powers are the same. Now, these are the leading terms, the highest power terms, and when you're plugging in really big numbers, the smaller power terms basically disappear in effect or size, and these guys take over. That's why we're only looking at the highest power terms. And since they're the same, that's that BETC, so we're going to use the coefficients, which is 1 to 1. So that means our horizontal asymptote is at y equals 1. Now, if we're wanting to find where the function equals or hits its horizontal asymptote, if it intersects it or not, what we're going to do is we're going to take the original function, which was x squared plus x minus 2 over x squared plus 3x minus 10, and set it equal to the horizontal asymptote, which is 1. And then try solving for x. We would need to multiply by the denominator with the 1 to bring it up top and get it off the bottom. And when we do that, we're going to get x squared plus x minus 2 equals x squared plus 3x minus 10. If you try moving the x squareds, they will cancel each other out. If you bring the x over to the right side, that'll give you 2x. And then take the 10 over to the left side, that'll give you 8. And so that means x equals 4. And since we have x equals 4, and over here we know the horizontal asymptote is 1, that means the point of intersection is at 4, 1. So that would be where it intersects it. So yes, it intersects it at the point 4, 1 would be how you would have to answer this question. Now when you get to number 4, 5, and 7, they start being top heavy and you have to do something else to find the end behavior asymptote. And you can see that number 4 says we're going to use long division to find the end behavior asymptote. And then it's going to ask, where does it intersect its oblique asymptote? Now, oblique asymptote is just another name for slant asymptote. And when you're doing this long division, remember, it's just the quotient that you use for the slant asymptote. Any remainders or whatever get thrown away. They're not part of the slant asymptote. However, when you want to find where it intersects that slant asymptote or oblique asymptote, that's where you do use the remainder and you set it equal to 0. Let me show you an example. Let's say we were dividing some polynomial into another polynomial, and the quotient ended up being x minus 5. This would end up being our slant asymptote or our oblique asymptote. And as you're working these things out, you may have a remainder of like 2x minus 4. In that case, when you're wanting to find if it intersects or not, just simply set the remainder equal to 0, solve for x. So x would be 2. Then you would take that value, plug it back in to your slant asymptote to find your y, and y would be negative 3. So that means the function would intersect the slant asymptote at the point 2, 3. So that's how you would find any intersection points when you're having to do long division, when it's top heavy.